All of these are in meters, so I'm going to avoid labeling them as meters. Okay, so this is kind of obvious to everybody. All right. Start off in an auspicious manner. Everything starts with 0. Okay, so at the first spot, M is 0 millimeters. This is the first value here. And think of all of these values as values you are marking on a plot. And you have a plot of x versus y. At x is equal to 2 meters, my y is 4. That's what I'm doing. At x is equal to 1 meter, my y value is 175, so I'm just marking that point there. They're all just points on a plot. There's nothing special about these things. They do tell us something nice later on. I go to the next step, which is 0 plus. What's this going to be? 0 plus and 0 minus. Do you see some couple moments at that point? I don't see anything there, so it has to be 0. So which means x is 0 plus is the same as x is equal to 0 minus, so I'll avoid writing that out. Next step. Watch out now. Now you are in the heat of the battle. You have entered the beam. As you enter the beam, you have to look out in two directions. One is the beam, one is the shear force line. Okay? So I'm going to start off at x is equal to 1 minus. What is this value equal to? The change in the bending moment diagram is equal to the area under the shear force diagram. So I have to look at the area of this first rectangular box. Watch out. Plus 175 times 1. So this is a positive quantity. This is the. Now you see why we need to have the shear force diagram to draw the bending moment diagram, right? Because everything is accompanied by the area. Yes, sir.
So like in this case, you don't think about it creates a clockwise moment, the 175 force. You're only looking at the area under the curve.
Absolutely, absolutely.
Okay.
So the only reason why I have this is to deal with sticky customers like that.
Okay.
Otherwise, I am good to go with only the shear force diagram.
Okay.
Absolutely. Yes,
Can
question.
you explain that one more time, how you got the 175 times 1?
Oh yes. So between 0 and 1 meter, the change in the bending moment has to be equal to the area under the shear force diagram.
Oh, okay.
So this is a rectangle of height 175 and width 1 meter.
Thank you.
All right. So M at these Newton meters. I'm going to go a little faster now. We're going to complete this problem. Then I go to the next step. Where do I go next? Do I go to 3? I don't go to 3. I go to 1 plus z, which is 2.75. Because if I'm going to go to 3, I have to be inclusive of the fact that there is a positive area and a negative area. If the shear force value is negative, that area is counted as a negative area. Why is this negative area? Because this is minus 25. Yes, sir.
Do we not go to 1 plus first?
Oh, 1 plus, absolutely, yeah. Thank you. And when x is equal to 1 plus minus, that's 0 because there is nothing happening there. Okay, so thank you, I'll complete that. So be careful, if you have a point of 0 crossing, do the change in the bending moment between the 0 crossing and the previous point first. Don't be fooled by this figure here. This figure is only for this creature here, this 200 Newton meter flow. Otherwise it is kind of useless. Okay? So M at x is equal to 2.75 minus 2.75, where do I get that from? 1 plus z. Z is 1.75. This distance is 1 meter, so 2.75. Minus m at x is equal to 1 plus is area of the triangle, half times 175 times 2.75. If you do the computation, yes, question.
Would that be 175 times 1.75?
Oh, 1%. Thank you. Yeah, absolutely. Yeah. Thank you. Right. So m at x is equal to 1 plus is 175. Then I'm going to add up this creature here. So it's going to be the following. M at is I think 328. 0.125. If I do the additions and so on. Keep trudging. 2.75 plus minus, there is not much of a difference. Plus and 2.75 minus is 0. Yes, sir.
I just had a question. So I noticed a pattern with the moments here that it doesn't matter if it's plus or minus, like 0 plus or 0 minus, it's usually the same. Is that always the case or not?
No, not yet. So that's why I'm following this convention. Things are going to go into a cartwheel when we hit this creature. Okay? So this is the same value, so I just proceed. Next stop is 3 minus. If you want, you can take the liberty of going to 3 plus. Yes.
Why didn't we do the m at x is equal to 2.75 minus? Why didn't we do that minus? You added the 175. Why didn't we subtract it?
Oh no, so this is a positive area.
Right.
So which is why I am saying it as plus half times 175 times 1%.
Oh, so we're adding them, we're not subtracting.
You're not subtracting, right. So if the shear force diagram is on the upper side of the x-axis, that's a positive area.
Right.
If the shear force diagram is on the bottom of the x-axis, negative.
And that's regardless of the fact that you put a subtraction symbol there.
Regardless of this one?
Yeah.
Oh yeah, so you can think of it this way. So m at 2.75 minus, sorry for the, it shall be right in here. I bring this to the other side.
Oh, okay.
That's going to be m at x is equal to 1 plus half times
Okay.
that. So it's an addition.
Okay. Thank you.
So I'm skipping some of these algebra steps in the hopes that we will proceed further with the problem, but please do let me know if it doesn't make sense. Now here's what I'm going to do. I don't need to go to 3 minus, I can directly go to 3 plus, because both of them are in the negative region. If you want, you can do 3 minus and then go to 3 plus as well, it's completely fine. I'm going to say m at x is equal to 3 plus, which is the same as x is equal to 3 minus, because there is no couple moment acting at that location, okay, because of that fact. Minus m at 2.75 plus, this is now a negative area triangle of length 2 minus z, so 0.25 minus half 25 0.25. Be careful, this is negative. I bring this guy onto the right hand side, this is a positive quantity. I'm going to see a reduction in my bending moment value. Okay? So m at 3 plus is going to end up being, I think, 325 newtons. This is the same as m at x is equal to 3 minus. No difference there. The reason being, there is no singular event taking place. There is no couple moment at 3 meters. You can do the same thing for the shear force diagram as well, which is what we're going to be doing from the next class onwards. Now we come to a special location on this beam where there is a couple moment acting. Which is why you need this guy in tandem with the shear force. Okay? So, I'm going to go from 3 plus all the way to 6 minus first. M at x is equal to 6 minus m at x is equal to 3 plus. Can somebody help me unpack this guy? What's this going to be equal to?
Area under the curve, which is -25.
Beautiful. Beautiful. So this is going to be 3 times 25 with the negative side. This is the 3 meters. Don't be fooled like you did for the shear force diagram. You're not looking only at this guy here. You're looking at the shear force diagram if you're drawing the bending moment diagram. So this is the area under the shear force diagram. So minus 3 times 25. So I'm at 6 minus will end up being, so that's 325, that's 75, so 275. Makes sense to everybody so far? Good.
Would it be 250? Because minus
250.
75.
325 minus, yeah. Sometimes I am that way. Thank you. All right, are you all ready for the next event? That event is taking place at x is equal to 6 plus, because between 6 minus and 6 plus I am seeing a couple moment. This couple moment is in what sense?
Counterclockwise.
Counterclockwise. When we did our derivations, the change in the bending moment is equal to a positive m naught value, where if we call this as m naught, only when the applied moment was clockwise. I particularly mentioned that to you. It's an anomaly there. Every time you think counterclockwise, positive thing, good things are happening, that's not the case. In the bending moment diagram, a counterclockwise couple moment pulls it down. Okay? So I'm going to write that next. I'm going to get rid of the 0 guy here. So everybody good to go on this? M at 6 plus 6 minus, this is equal to minus m naught, which is minus 200. Negative sign, please make sure you're getting that idea right. We did the derivation, so I'm not going to go back and do it again, but counterclockwise couple moment distorts the bending moment diagram down. Okay? Do the math. X is equal to 6 plus. E is going to be 250 minus 200, so that's 50. Go all the way home. That's my next stop. 8 minus and 6 plus. What is this going to be?
Minus 6 plus is equal to 15 or negative 50, right?
Negative 50, right? Because that is the area under the shear force diagram. So this is 2 meters here. Minus 25. Minus 25 times 2 is minus 50. I'm going to clean up this figure. This is probably the only disadvantage of writing on the board. If the other boards are not working, I have to keep erasing frequently. I'll get the thing working hopefully soon. So m at x is equal to 8 minus is 6 plus is 50, this is minus 50, so they end up becoming equal to 0. So I'm back home, I don't need to bother about 8 plus, it should be the same. I'm going to draw this out, okay, and we're going to come and make sense of it. We want it to be lower. Can everybody see until here? Okay. This is m in Newton meters. This is x in meters. Start off at 0, so it was 0. The shear force and the bending moment diagram, they have to be drawn one below the other because they have a significance, right? One is the integral of the other. The bending moment diagram is the integral of the shear force diagram, essentially. You're thinking of it that way, right? I start at 0, then I go all the way at x is equal to 1 minus, I go to 175 Newton meters. How do I go? I need to go here. How do I go from 0 to 175? Do I go as a straight line? Do I go as a curve? Straight line is also a curve, but do I go as a quadratic or a cubic? I go as a straight line because the slope of the bending moment diagram is equal to the shear force value. If the shear force value is a constant, this is a constant slope. Then comes the interesting part. At 2.75, I am sitting at 328.125. Okay, so this is somewhere here. 328.125. Just want to complete this. How do I go from here to there? Is the next question that we need to answer. I'm not going to answer that question in today's class. I'm going to draw the curve. I'm going to let you figure it out. We're going to come back on Wednesday and then try to complete this talk. Okay, so here's what happens. Slope of the bending moment diagram is equal to the shear force value. The shear force value is positive but decreasing from 1 to 2.5. So which means the slope of my bending moment curve should be positive and decreasing. So I start off at the slope here, that has to be continuous, and then I draw it as a quadratic. Okay, this is a quadratic. Ends up as a 0 slope because the value of the shear force becomes 0 at that point. Then from there on to the next point, I am still going as a quadratic because the shear force is changing linearly. The bending moment has to be a quadratic. It has to be the next higher derivative, right, of the shear force. So I'm going to go down a little higher up. I'm sorry. That's not where I wanted to go. So somewhere here. This is a continuous slope. I just drew it as discontinuous because of my poor choice of heights. So it's a continuous slope. Then I fall down to 325. Fall down in a quadratic manner as well. Then from 325, I have to go all the way to 250. That is from 3 to 6 meters. I go in a linear fashion. And then all the way from 250, I have to go to 50 Newton meters. And that's also in a linear fashion. Okay. That's a jump, I'm sorry, that's a jump right down here. So this is the jump that you see in the bending moment diagram. Okay, this is because of the fact that I'm sitting at x is equal to 6 plus. It's dragging me down to 50 Newton meters. And then I go down. Okay, so this is 50. And this entire creature is the bending moment. I did not do justice to it today. I went through it a little fast. I'm going to come back. We're going to start with this with all the values written down, and then I'm going to explain some of these steps again. Okay? Quickly. Thank you.
At this point, we have to disclose it.
I see ya.